Okay, welcome to the webinar, everyone. We had some technical difficulties to begin, but I think we have those ironed out. PySec Institute conducts these webinars from time to time on an irregular schedule, and normally our webinars are reserved for students, but in this case we have a presenter with an especially interesting topic, and it's also Master Black Belt for the PySec Institute. His name is Larry Dyer. Larry and I worked together on a number of projects in the past, and he has gone through PySec Institute Master Black Belt certification, as well as being a Master Black Belt for his employer. So today's topic is the individual and moving range chart, and just to give you a little mechanical overview, you're all muted right now because usually there's too much background noise if I put you all on audio, but I can unmute you one by one. So if you have a question, you can type it into the question window. I'll unmute you. You can ask the question, and we'll hopefully be able to manage this webinar in a way that works for everyone. And we'll answer your question, of course, using the audio system. So I'm going to turn over control to Larry, and he is going to talk to you about the individuals and moving range chart. And he's also going to talk about one of the competitors to that chart, the XBAR and R chart, or averages and ranges chart. So Larry, here you go.
Okay. There. Can you see that, Tom?
Yep, we see it perfectly.
Okay, great. All right. So we're going to talk about the individual and moving ranges chart. And I need to talk about the XBAR partly when we do that, just so that you'll understand what's going on and the differences here. Let's move on to the next slide. This is a pretty typical slide that you see when people start talking about the different kind of charts that are available. And the one in particular, the two in particular that we're going to talk about is the IMR and the XBAR. And as you can see, they both require continuous data, and really the difference is the subgroup size. So the IMR chart uses a subgroup size of 1, and the XBAR uses typically 2 to 9 for a subgroup size. So the individual chart is control chart for variable data. It's for continuous data, monitors the process over time, and you'll see through this, I mentioned a couple times that we're using time-ordered data, and it plots the measurements as a separate data point for each value, and so each data point stands on its own, group size of 1. And then the moving range chart uses a default value of 2, which means that we're looking at the range between the different points on the chart. You can change that. Typically people leave it at 2 though. And so there will be one less data point on the moving range chart than there will be on the IMR chart, on the I chart. This is just an example of an IMR chart taken from Minitab, and you can see on this one where you have the points that are out of range above the control limits, and you can see that there's a big difference in those points, and that is also reflected in the moving range chart at the bottom. So when you've got a dramatic change in the points on the individuals chart, you're going to see that change also on the moving range chart. And that just shows you the different points that we're talking about there. So now let's talk about the XBAR chart. What's the difference? Well, it's a control chart for variable data once again, and it monitors the process over time. But the distributions need to be approximately normal, and it's based on the average of a series of observations. We call that a subgroup. Monitors the variation between those observations. And the larger the subgroup, the more sensitive the chart will be, providing you have a rational subgroup. And so the question is, well, what's a rational subgroup? Well, a rational subgroup is, these are items that are produced under essentially the same conditions. Typically, they're consecutive. So you're talking about a series of observations consecutively that each become a subgroup. So if you look at a stable distribution, and this distribution is made up of individual readings, and those readings, as soon as this paints, there we go. So you can see you have one subgroup that's black, and those readings occur all over this distribution, but they are occurring in a time-ordered sequence, so they're occurring sequentially. But the readings can come from anywhere in the distribution. So that's where rational subgroups come from. So here's just an example of an XBAR-R chart, and we're going to talk about these in a little more detail.
Question,
yeah.
Larry? That XBAR-R chart, is that the same data that you use in the IMR chart you showed earlier?
Let's go back and see. I believe it is. No, this is blood pressure. Yeah, okay. But I've got some further on that are the same data that will show that. Let me get back to where we were.
Sorry.
No problem. No problems. So when do you use an IMR chart? When you have a limited number of individual measurements. Where I work, we have very few opportunities to use an XBAR-R because you just don't have enough data. We're collecting one data point a week or one data point a month. It just doesn't work. Now, we do have one area where we can do that, where we actually calculate the cost of a bill, and we do millions of those. Now, that's a great opportunity to use XBAR-R or even the XBAR-S chart. But typically, you don't have that amount of data, so that's why the IMR chart is so useful. So, but you do use the XBAR-R when you can have subgroups of 2 to 10. If your subgroups are larger, you use the XBAR-S, and which is a little more sensitive.
Larry?
And once again, yeah.
We have a question from Burhan, and I'm going to unmute him if you're ready to take his question.
Sure.
Okay. All right, Burhan, you're on the air. Okay, it's like a radio talk show, I guess. So Burhan, I've unmuted your microphone, and you can go ahead and ask Larry your question, or otherwise you can type it into the window if we can't get your audio to work.
Have I heard my name mentioned? Hello?
Yeah.
Yeah, hi. Burhan,
I didn't have a question. I don't know where that came from. I'm just listening.
Oh, okay. I'm going to go ahead and mute you again. Go ahead, Larry. Sorry, Burhan. Didn't mean to shock you.
Well, they can always type a question, and you can let me know what it is, Tom.
Yeah, that works too, folks.
Okay. So once again, the data is time ordered. The difference here between the IMR and the XBAR are individual measurements, subgroup measurements. Pretty straightforward. So when you're interpreting these, you always start first with the R chart to interpret them. Whether it's an IMR or the XBAR-R, you look at the R chart first, and you're going to look at the control limits, and you're going to see if the data is in control on the moving range chart. And if it's out of control, then the control limits on the individual and the XBAR-R chart are going to be meaningless. So you need to fix that first. So you need to look for any special causes of variation. A couple of rules of thumb: you should see more than 5 distinct values plotted on your moving range chart, and no single value should appear more than 25% of the time. You might not have enough detail or getting the level of detail you need on your readings if you've got a lot of the same values down there. So here's an example of an individual chart, and you can see that there's a big change in 2 values on this chart. Now the chart says it's in control, but the moving range chart shows a point out of control. And what that's telling us is that there's too much change in my individual chart to make that random. Okay, the software is believing that this is not a random event because of the amount of change I had in my individual chart. Okay, so then average charts become more sensitive to process changes as the subgroup size increases. Well, what does that really mean? Okay, so let's take a look at, this is the same data, and the chart on the left shows glucose readings with a subgroup size of 3, and the chart on the right shows the same data with a subgroup size of 9. Now you can see at the bottom I put the range in there for the upper and lower control limits on both of those, and you can see that the control limits on the subgroup 3 chart are narrower than the control limits on the subgroup of 9 chart. So that means that there's better discrimination on the subgroup of 9 chart. And you can see also there's one out of control point on the subgroup size of 3 chart on the top for the X bar. And that I would call that an unfortunate choice of subgroup size. When you make these subgroups, then the upper and lower control limits are going to be tighter than from the individual chart. So in this case, this one just popped above the line. So then interpreting the individual chart. So now we're going to look at the top chart. We've got the bottom chart in control. Now we want to look at the top chart. So you want to look at it relative to the control limits and the run tests. And what are run tests? The run tests are some people call them run tests, some people call them the Western Electric rules, and I've got those on here. Let's see if I can bring that up. Is that going to drop to that?
I think it took a while when we rehearsed this too, Larry.
Oh, to actually, okay.
We're waiting for the art.
Oh, we were waiting for the art. Okay, so I'll just go ahead and finish this slide and then I'll get to the run test. So what you want to do is look for out of control points, and the point here is that if you're using an X bar R chart, it cannot be compared to the requirements. So what do I mean by that? We'll go to the next slide. Come on, next slide. It seems to be getting slower, Tom.
Yeah.
Okay, there we are. All right. So this is once again the same data. This is glucose readings. You can see on the individual chart on the left and the subgroup size of 9 on the right. And once again, we want to look at the control limits, but now we're looking at the top chart control limits. And you can see that the control limits for the IMR chart are much wider than the control limits for the X bar R chart. So if I've got individual readings up near the control limit on the IMR chart of 131, and I set my requirements at 109, which is what the X bar R chart says, then I'm going to have things that are out of control show up, and my customer is not going to be satisfied. So that's the whole point of, you can't use the X bar R chart when you build your requirements or when you set your customer specification.
Comment? Another thing is that the customer feels the individual experience. They don't really feel the average. So,
yep.
The average is something that we can use for process control and to detect changes and special causes in the process. But from the customer's point of view, their individual experience is what counts, and that's what shows up on the eye chart.
Good. Good. So it's real easy to construct the IMR chart. I mean, you just have to figure out, what am I going to collect data about? Then the purpose of the chart, set up your data collection points, and like I said, rarely do we have opportunities where we have enough data where we could even use the XBAR-R. Determine if you need any special measurement method or criteria, and then drop it into Minitab or some other charting tool. It's pretty simple. Then this chart, this was the run test, and these are the special conditions that have been identified over the years as being something that is other than random. And so I just included these because these a lot of people don't know what all of these are. So
comment?
Yes, go ahead.
So these run rules are designed so that any given run rule has about the same probability of occurring in random data as a point being outside of the control limits. And while they're very handy to use for offline analysis, I never apply them in real time. And I use them in team situations just to really look for patterns that might help us put things on the cause and effect diagram, or might help us find CTQs that we can use for experimental design.
Yeah, where we've used these is when we're trying to determine if a process change occurs. So that's been very helpful, because then it highlights it in red, and you can point that out to management.
Mm-hmm. One of the problems with using them for real-time troubleshooting is that, let's say you take the 15 consecutive observations within a standard deviation. Whatever change happened occurred 15 observations ago, and the time lag makes it very difficult to identify those causes. So you don't really want to stop the process while you look for something that's going to be so hard to find. Any questions? Okay. Let's give you a moment of silence and time to type in your question. And Paul, I see you have a question. Do you want to type it in, or would you like to have the microphone? I've unmuted you, Paul, so go ahead.
Well, I was just thinking about that chart with the 15 observations within one standard deviation. And I'm a little bit confused as to why something would be wrong with that. Because I'm looking at that and I'm saying, oh, this looks great.
Do you want me to take it, Larry?
Control, and it's very tight around the center, so I'm a little bit lost there.
So I understand what you're saying. It's like, well, this is actually good, and so why do we call it out of control? Is that the question?
Yes. Why do we have a problem with it?
You want to take it, Larry, or you want to give me a shot?
Yeah, I'll start. What that tells me is there's a specific cause for that. That's what this chart is trying to get you to understand, is something specifically happened, some special cause, similar to when a data point is outside of the control limits is a special cause. You have anything to add, Tom?
Yeah, it's what's happening there, Paul, is a control chart doesn't tell you when something's necessarily gone wrong. It'll also tell you if something's spontaneously gotten better. So perhaps that's what happened here is, we had a process change that made the process better. So, for example, maybe the control chart was based on several different suppliers providing input, and somehow we got a single supplier, and that made the process more stable. So that's one thing that had happened. So this pattern would tell you that, take a look and see why your process got better, and perhaps it's something that you can lock in and do continuously.
Okay.
More often what I've seen is that it involves stratification of the data. So what I've seen, when I've seen this occur most often is if, let's say, for example, we have several different people involved in the process when we set up our control chart, and we end up sampling from the same person all the time. That would create this kind of a pattern. Or if we set up our process control limits, let's say if we have a multiple station machine sampling from all of the different stations on the machine, and then we have a sampling pattern that we don't really want. So for example, I saw a situation where there was a machine with 4 workstations, and after the control chart went onto the process, people start sampling 1 out of 4. And so they're always sampling the same workstation, and this pattern occurred, and it was really something that we needed to revise our control chart sampling procedure.
Okay, so what I'm supposed to take away from this then, if I'm understanding you, is that the control charts are not necessarily looking for problems in the system, but they're looking more for changes in the system.
That's right. A control chart is the operational definition of a special cause of variation. All it'll tell you is that there is a special cause, and you'll want to find out what that cause is so that you can either lock it in if it made the process better, or fix it if it made the process worse.
Okay, I get that.
Okay?
So in the case that Tom mentioned first, where you have multiple vendors and you go to a single vendor, in that instance, that's a special cause. It's a change in your process. And I have seen this, as Tom mentioned, I have seen this when you are looking at individuals and you're looking at the performance of individuals. And sometimes you'll see this.
With that same logic, well, some of that hold for the 14 consecutive observation alternating up and down?
Well, what that involves is a special cause that is called mixture. So what happens is that if you have that problem, your 2 samples are correlated with one another, and they're telling you that there's a pattern in your data. So one place I saw that occur was that we, in the electronics industry, they have parts that are called axial parts. So a resistor, for example, will have a wire coming out of each end. And the process I saw was measuring the distance from the end of the left side of the wire to the resistor, and then from the right side of the wire to the resistor. And what happens is that if I make the left end shorter, the way that the ends are trimmed, if I move the resistor to the left, then the left side will be shorter and the right side longer. If I move it to the right, then the left side will be longer and the right side shorter. And if you measure the 2 and put them on a control chart, you're going to get that alternating up and down pattern.
Okay, so this can happen in for example, in a process where there's indexing.
Yeah, that's right. And it could also happen if you have, if you're sampling from 2 different workers and they have 2 different performance levels. So, person A is higher, person B is lower, and it's alternating up and down. So
that would be a stratification problem there again.
Right. It'd be a problem of stratification and mixture. So you have 2 distributions together. Your sampling pattern is stratified, and the process is a mixture of 2 cause systems.
Okay, great.
Okay?
Thank you. Thanks.
You bet. Any other questions? Just go ahead and click the raise the hand button. I'll see it and unmute your mic for you. So I'd like to make a comment on way back at the beginning of your presentation there, you had a chart that I know came out of the Six Sigma handbook and showed how to select these, how to select a control chart. I think it's like maybe your first or second slide. Challenging, isn't it? Keep going. It's that decision tree. That's what I'm looking for. There we go. So if you look at that decision tree, it says that you have attribute data on the left and continuous data on the right. But we often use the individuals chart for attributes data. And I just wanted to comment that you can do that. So if you're plotting defects or defectives and you have, let's say you're looking, Larry's in the insurance business, let's say you're looking at errors on applications. You should, or the correct quote-unquote chart for that might be the C chart if you're counting errors, or the NP or P chart if you're counting applications with errors. But you could actually plot that data on an IMR chart, and it would work pretty well in most cases. In fact, some cases it'll work better than the quote-unquote correct chart. So if you have a lot of variation between samples and that variation is normal for your process, the attribute control charts would show your process as being out of control if you had a large sample size, and it would be perhaps an amount of variation that was of no practical importance. And you should, in those cases, use the iChart to plot those data, just because the iChart's only going to show you changes that have some economic meaning.
We have used this, Tom, when we get a form called a healthcare 1500 form, and accounting defects on forms. We've used it for that.
Okay, any other questions? Well, if not, I'm going to thank you all for attending, and thank you, Larry, so much for presenting. And at this point, I'm going to end the meeting. I will be sending everyone a link. Oh, I do have a question here. Paul, go ahead. I've unmuted you.
Well, I think it's maybe what you're about to mention. I was just wondering if this presentation would be saved somewhere on the website.
Yes, I'm going to upload this presentation, and I will post a link to it on sixsigmatraining.org and in the blog. So if you go up there and search for Swiss Army Knife or webinar, you'll be able to see the link to the video up there.
Great.
Okay, thank you. So, and I'll also send a link to the presentation to each of you, and I want to thank you all for attending, and hopefully we'll see you at future webinars, and thank you so much for presenting, Larry. Great job.
Oh, you're welcome. Thank you.